A data matrix code is a two-dimensional matrix barcode consisting of black and white cells, or modules arranged in either a square or rectangular pattern. The information to be encoded can be text or numeric data. Usual data sizes from a few bytes up to 1556 bytes. The length of the encoded data depends on the number of cells in the matrix. Error correction codes are often used to increase reliability. Even if one or more cells are damaged so it is unreadable, the message can still be read. A data matrix symbol can store up to 2,335 alphanumeric characters. Data matrix symbols are rectangular in shape and usually square and are composed of cells, little squares that represent bits. Depending on the coding used, a light cell represents a 0 and a dark cell is a 1, or vice versa. Every data matrix is composed of two solid adjacent borders in an L shape and two other borders consisting of alternating dark and light cells, or modules. Within these borders are rows and columns of cells encoding information. The finder pattern is used to locate and orient the symbol, while the timing pattern provides a count of the number of rows and columns in the symbol. As more data is encoded in the symbol, the number of cells increases. Each code is unique. Symbol sizes vary from 10A, 10 to 144A, 144 in the new version ECC 200, and from 9A, 9 to 49A, 49 in the old version ECC 000-140. Applications. The most popular application for data matrix is marking small items, due to the Codia unregistered trademark S ability to encode 50 characters in a symbol that is readable at 2 or 3 UMDU, and the fact that the code can be read with only a 20% contrast ratio. The data matrix is scalable, with commercial applications as small as 300 micrometers and as large as a 1 meter square. Fidelity of the marking and reading systems are the only limitation. The United States of America's Electronic Industries Alliance recommends using data matrix for labeling small electronic components. Data matrix codes are becoming common on printed media such as labels and letters. The code can be read quickly by a barcode reader, which allows the media to be tracked, for example when a parcel has been dispatched to the recipient. For industrial engineering purposes, data matrix codes can be marked directly onto components, ensuring that only the intended component is identified with the data matrix encoded data. The codes can be marked onto components with various methods, but within the aerospace industry these are commonly industrial inkjet, dot peen marking, laser marking, and electrolytic chemical etching. These methods give a permanent mark which can last up to the lifetime of the component. Data matrix codes are usually verified using specialist camera equipment and software. This verification ensures the code conforms to the relevant standards, and ensures readability for the lifetime of the component. After the component enters service, the data matrix code can then be read by a reader camera, which decodes the data matrix data, which can then be used for a number of purposes, such as movement tracking or inventory stock checks. Data matrix codes, along with other open-source codes such as 1D barcodes, can also be read with mobile phones by downloading code-specific mobile applications. Although the majority of these mobile readers are capable of reading data matrix, few extend the decoding to enable mobile access and interaction, whereupon the codes can be used securely and across media. For example, in track and trace, anti-counterfeit, EGOVT, and banking solutions. Food industry, data matrix codes are used in the food industry and auto-coding systems to prevent food products being packaged and dated incorrectly. Codes are maintained internally on a food manufacturer's database and associated with each unique product, for example ingredient variations. For each product run, the unique code is supplied to the printer. Label artwork is required to allow the 2D data matrix to be positioned for optimal scanning. For black and white codes, testing isn't required unless print quality is an issue, but all color variations need to be tested before production to ensure they are readable. Art. In May 2006, a German computer programmer, von Hoppenger Currency RTNER, created a large data matrix in a wheat field. The message read "Hello, world." In June 2011, the Parisian tattoo artist KARL, as part of a promotion for Ballantine's Scotch whisky, created the world's first animated tattoo utilizing a data matrix code in a collaborative process streamed live on Facebook. Technical specifications. Data matrix symbols are made up of modules arranged within a perimeter finder and timing pattern. It can encode up to 3,116 characters from the entire ASCII character set. The symbol consists of data regions which contain modules set out in a regular array. Large symbols contain several regions. Each data region is delimited by a finder pattern, and this is surrounded on all four sides by a quiet zone border. Data matrix ECC200. ECC200 is the newest version of data matrix and uses Reed-Solomon codes for error and erasure recovery. ECC200 allows the routine reconstruction of the entire encoded data string when the symbol has sustained 30% damage, assuming the matrix can still be accurately located. Data matrix has an error rate of less than 1 in 10 million characters scanned. Symbols have an even number of rows and an even number of columns. Most of the symbols are square with sizes from 10A, 10 to 144A, 144. Some symbols however are rectangular with sizes from 8A, 18 to 16A, 48. All symbols utilizing the ECC200 error correction can be recognized by the upper right corner module being the same as the background color. Additional capabilities that differentiate ECC200 symbols from the earlier standards include inverse reading symbols, specification of the character set, rectangular symbols, structured append, data matrix ECC000-140. Older versions of data matrix include ECC000, ECC050, ECC080, ECC100, ECC140. Instead of using Reed-Solomon codes like ECC200, ECC000-140 use a convolution-based error correction. Each of these varies in the amount of error correction they offer, with ECC000 offering none, and ECC140 offering the greatest. For error detection at decode time, even in the case of ECC000, each of these versions also encode a cyclic redundancy check on the bit pattern. As an added measure, the placement of each bit in the code is determined by bit placement tables included in the specification. These older versions always have an odd number of modules, and can be made in sizes ranging from 9A, 9 to 49A, 49. All symbols utilizing the ECC000-140 error correction can be recognized by the upper right corner module being the inverse of the background color. According to ISO IEC 16022, ECC000-140 should only be used in closed applications where a single party controls both the production and reading of the symbols and is responsible for overall system performance. Standards. Data matrix was invented by International Data Matrix, Incorporated, which was merged into a VSI QTCI matrix, who were acquired by Siemens AG in October 2005 and Microscan Systems in September 2008. Data matrix is covered today by several ISO IEC standards and is in the public domain for many applications, which means it can be used free of any licensing or royalties. ISO IEC 16022-2006 a Euro data matrix barcode symbology specification, ISO IEC 15415 a Euro 2D print quality standard, ISO IEC 15418-2009 a Euro symbol data format semantics, ISO IEC 15424-2008 a Euro data carrier identifiers, IDs for distinguishing different barcode types, ISO IEC 15434-2006 a Euro syntax for high-capacity ADC media, ISO IEC 15459 a Euro unique identifiers, encoding. The encoding process is described in documents published by ISO website. Open source software for encoding and decoding the ECC200 variant of data matrix has been published. The diagrams below illustrate the placement of the message data within a data matrix symbol. The message is Wikipedia, and it is arranged in a somewhat complicated diagonal pattern starting near the upper left corner. Some characters are split into pieces, such as the initial W, and the third I is in corner pattern 2 rather than the usual L-shaped arrangement. Also shown are the end of message code, the padding and error correction bytes, and 4 modules of unused space. There are multiple encoding modes used to store different kinds of messages. The default mode stores 1 ASCII character per 8-bit code word. Control codes are provided to switch between modes, as shown below. Text modes: the C40, text and X12 modes are potentially more compact for storing text messages. They are similar to DEC RAID X50, using character codes in the range 0 and 3 of these codes are combined to make a number up to 40 Aries cubed equals 64,000, which is packed into 2 bytes as follows: V equals C1 1600 plus C240 plus C3 plus 1, B1 equals floor, V/256, B2 equals V mod 256, the resulting value of B1 is in the range 0 249. The special value 254 is used to return to ASCII encoding mode. Character code interpretations are shown in the table below. The C40 and text modes have 4 separate sets. Set 0 is the default, and contains codes that temporarily select a different set for the next character. The only difference is that they reverse upper and lower case letters. C40 is primarily uppercase, with lower case letters in set 3. Text is the other way around. Set 1, containing ASCII control codes, and Set 2, containing punctuation symbols are identical in C40 and text mode. EDIF-ACT mode. EDIF-ACT mode uses 6 bits per character, with 4 characters packed into 3 bytes. It can store digits, uppercase letters, and many punctuation marks, but has no support for lowercase letters. Base 256 mode. Base 256 mode data starts with a length indicator, followed by a number of data bytes. A length of 1 to 249 is encoded as a single byte, and longer lengths are stored as 2 bytes. L1 equals floor, length /250, plus 249, L2 equals length mod 250. It is desirable to avoid long strings of zeros in the coded message, because they become large blank areas in the data matrix symbol, which may cause a scanner to lose synchronization. In order to make that less likely, the length and data bytes are obscured by adding a pseudo-random value r, n, where n is the position in the byte stream. r, n, equals mod 255 plus 1, patent issues. Prior to the expiration of U.S. Patent 5,612,524, intellectual property company Acacia Technologies claimed that data matrix was partially covered by its contents. As the patent owner, Acacia allegedly contacted data matrix users demanding license fees related to the patent. Cognex Corporation, a large manufacturer of 2D barcode devices, filed a declaratory judgment complaint on March 13, 2006 after receiving information that Acacia had contacted its customers demanding licensing fees. On May 19, 2008 Judge Joan N. Erickson of the U.S. District Court in Minnesota ruled in favor of Cognex. The ruling held that the 524 patent, which claimed to cover a system for capturing and reading 2D symbology codes, is both invalid and unenforceable due to inequitable conduct by the defendants during the procurement of the patent. Notably, since the 524 patent expired in November 2007, a ruling against Cognex wouldn't have affected current use of data matrix codes. However, it would have established that use of data matrix prior to November 2007 could potentially be covered by the 524 patent. A German patent application DE 4,107,020 was filed in 1991, and published in 1992. This patent is not cited in the above U.S. patent applications and might invalidate them. See also, Aztec code, high-capacity color barcode, Marxi code, Nintendo e-reader, QR code, semicode, Spark code, trusted paper key, references. External links. GS1 Data Matrix, An introduction and technical overview of the most advanced GS1 application identifies compliance symbology.